Frequency modulation we are going to discuss here. And if you see that on the basis of beta, that is the modulation factor, will have two different types of the FM. That is narrowband and wideband FM. Apart from this, we are going to see that transmission bandwidth calculation, that is with the help of Carson's rule, as well as if you see that there how we have power, and in case of FM, and apart from this, we have discussion about the Jacobian function also, and some important numericals that they're asking repeatedly. So still you didn't subscribe our channel, please subscribe it and share with your friend. So already you are aware it is the frequency modulation. In the previous lecture we have seen about phase and frequency modulation introduction. Here we are going to see in more detail about what is the frequency modulation. Means here amplitude is going to be constant and it is the non-linear function where we have m of t is going to be the modulating signal or message signal. So this modulated wave of FM, that is S of t, is going to become the nonlinear modulation process. So here, what will be constant? Phase is going to, phase we are not talking here. We are talking in terms of frequency. So amplitude will be the constant, and in case of modulated wave, what we are going to obtain, the frequency of the carrier signal is going to change according to instantaneous value of this message signal. So here we are talking about single tone, means we are considering only one modulating wave. So only one frequency will be available, that is FM, for this message signal. So here later we'll have two different types. One will be the narrow band, another will be the wide band. If beta will be less than 1, that will be called as the narrow band. And when beta will be greater than 1, that will be called as the wide band. What is the beta? Beta is the modulation index. Later we are going to see. So in this question, they're going to ask you here, derive the expression for the narrowband FM or wideband FM, anyone they're going to ask. Okay, so narrowband FM is more important compared to wideband FM. So here message signal is considered as the AM cos 2 pi FM t. So here we are trying to find the instantaneous value, since if you see that modulated wave is given as AC cos of theta I of t. So with the help of Fi of t, we'll try to find the theta I of t here. So this Fi of t, that is the instantaneous frequency, is given as Fc plus Kf into M cos 2 pi FM. So this is M of t, our message signal. So finally Kf into M is going to become del F, that we call as the frequency deviation. So this is the 1 marks question will come, define the frequency deviation and write the expression of the frequency deviation. So del F is what here? Kf into AM. Okay, so what you see here, Kf is the frequency sensitivity here. So AM is the amplitude of the message signal. So you see that del F is the proportional to the amplitude of the message signal, and it is independent of the frequency of the message signal. Okay, so that we have to keep in the mind. So now how we'll find the theta I of t from here? So we are going to multiply this instantaneous frequency by 2 pi and we are going to integrate. Okay, so here in the integration part, what we have, this is the Fi of t. So Fi of t value, what we have? 2 pi Fc. So it is going to be integrated after we are multiplied by 2 pi here. Okay, and it is going to be integrated here. Apart from this, what we have here, that is Kf into AM is the del F. Then you have cos 2 pi FMT. This is going to be becoming integrated with respect to t. So finally we'll have here 2 pi Fc t. Okay, 2 pi Fc t. So finally, how we are going to obtain the value? This is the del F, and integration of the cos is going to become the sine with respect to 2 pi FMT. Then here, this is the FM, so it is being divided here by this 2 pi FM, and this 2 pi is here. Okay, here also 2 pi is there, 2 pi here. So this 2 pi get cancelled. So finally, what we are getting here, del F by Fm. So this del F by Fm is going to be the modulation index here, that is the beta. Okay. So beta is what here? Del F by Fm. So this is also called as the phase deviation. So that frequency deviation, what we have seen earlier, del F shows that this modulated wave is going to be deviated how much from the carrier frequency. So that is going to be represented by the frequency deviation. So now finally we got here theta I of t, that is 2 pi f c t plus beta sine 2 pi fm t. So hence modulated wave is AC cos theta I of t. So theta I of t value is substituted here. Now we have, if beta is going to be less than 1 radian, it is the narrowband FM. If beta is greater than 1 radian, it is going to be wideband FM. Now we are going to see separately what is the how we are going to obtain the narrowband frequency modulated wave, and later we'll see how we'll obtain the wideband frequency. So here we are going to consider for this narrow band. So beta is taken as less than 1, and this expression what we have for the modulated wave. So in that modulated wave, if you see, we have expression for the cos A plus B. So this is taken as the A and this is being taken as the B. So now we'll apply the formula of the cos A plus B. That formula is what we have: cos A into cos B minus sine A into sine B. Okay. So once we'll substitute A as the 2 pi fct and B as the beta sine 2 pi fmt. So now here beta is considered less than 1. So beta is considered less than 1. So this value is going to be the less than 1. So in case of cos theta, if theta is less than 1, then cos theta value is going to be equal to the 1. Okay, since we have, if theta tends to 0, that is cos 0 is what? 1. Whereas in case of sine theta, if theta is much smaller, the sine theta is going to be equal to the theta. So on the basis of this, cos beta of this is written as the 1, whereas the sine beta of this is taken as the beta sine 2 pi fmt. So finally, we'll have simplified form of this one. So that is the equation number 2. Now we are seeing that how we can represent equation number 2 with the help of block diagram, how we are going to obtain. Before already we have discussion how to obtain the frequency modulation from the phase modulation. So that also we are going to use the integrator. So what is happening here? Modulating wave is given input to the integrator. So modulating wave is what? Baseband signal or message signal that is given to the integrators. So integrated output of this one is given to the product modulator. Okay, so here message signal what we are taking, message signal for us is the AM cos 2 pi FMT. Okay. So finally integration of this, what we are going to get here, sine. Okay, sine 2 pi fmt we are going to obtain here, and it is given to product modulators. Another we have carrier signal AC cos 2 pi fct. So directly it is given to the summer, and another is given to the with the minus 90 degree phase shifter to the product modulator. So the input to the product modulator is what here? AC sine 2 pi fct. So one input is now AC sine 2 pi fct to the product modulator. Another is the integrated output here. So that is going to be give us DSVSC signal here. Okay. And now if you see that part we are going to obtain in this format. Okay. So that's why it's taken with the minus sign, and AC cos 2 pi fct is the direct carrier signal that is given with sum. So finally we'll get here narrowband FM wave. So now those things again it is written here, okay, in detail how we are going to obtain and what are the things, and later here we are going to consider this one with going to compare in terms of AM signal. So here you are seeing that this is in case of FM, envelope is going to be constant, but here we have discussion about DSVSC, that is output of the product modulator. So that's why we are going to compare with AM also. So in case of angle modulation, theta of t is the harmonic distortion. Okay, that will have some in the form of third and order or higher order. It's not going to be completely noise free, so it will have some distortion also. But if beta is less much or equal to 0.3, then in case of this, it is limited to some particular values. So now if you see that here we have this is the S of t, that is going to be the part of the modulated wave. So that is the situation here. We have that sine A sine B, that is written in the form of cos A minus B minus cos A plus B. So that formula is applied here. So A is here 2 pi fc and 2 pi fm is the B here. Similarly, we have M modulated wave signal. So that is also being compared both here. And you'll see that what is the comparison between this. Sometimes they're asking compare the AM and FM. So this is the how we are going to represent the narrowband FM, and this is how we are going to represent the AM wave. So here we have with the help of upper sideband, lower sideband. Okay. Now we are going to discuss about wideband frequency modulation. So in case of wideband frequency modulation, beta value is what? Greater than 1. Okay. So here again, same modulated wave, AC cos 2 pi fct beta sine 2 pi fmt is taken. So it is the non-periodic unless carrier frequency is an integral multiple of FM. Okay. Then it will become the non-periodic. If it is multiple of the FM, integral multiple of FM, then it is going to be the periodic signal. And FC, you already know that carrier frequency is compared, it is taken much larger in compared to FM. Okay, at least 10 times, 20 times higher going to take. And here, so FC is again, it is larger in compared to bandwidth of the FM signal also. So this already you have discussion, you know about e to the power I theta, that is written as the cos theta plus I sin theta. So here what we have? Cos theta. So cos theta is the real part, sin theta is the imaginary part. So that's why we are writing real part of AC exponential j 2 pi fct plus beta sine 2 pi fmt. Again, we are going to separate here e to the power this one separate and e to the power this one separate we are going to write. So that apart from this, what we have AC into e to the power j beta sine 2 pi fmt is taken as the approximate of t. Another already exponential j 2 pi fct is written as it is. So this s cap or s approx of t is what here? It is the complex function of, okay, complex envelope of FM modulated wave. So that is written as AC exponential j beta sine 2 pi fmt. So now what we have seen that it can be the periodic function of time. Then what we can write in the form of complex Fourier series. So this is going to be the summation over n equal to minus infinity to plus infinity Cn exponential j 2 pi fn t. So now here we are going to see what is the Cn value in this case. So Cn is what here? Complex Fourier coefficient. So how we are going to obtain? It is Cn equal to Fm. Now we have integration over the limit minus 2 Fm to the plus Fm by 2. So that is the S of t approximate exponential minus j 2 pi Fn t into dt. So here sign is what here? Minus. So again, if you see that here, we are going to substitute the value of this. So that is the AC exponential j beta sine 2 pi fmt. So what we are seeing that AC is constant, so it is taken outside. Okay, so this is again exponential. So when we have e to the power a, suppose, and e to the power b, we can write e to the power a plus b. So on the basis of this, we are getting this part. Now here, we are going to take x as the 2 pi fmt. So on the basis of this equation 4 can be written in the simplified form. So it is the function of time here. So again, if you are going to take this is the dx by dt of this one. So what we are going to get here? 2 pi fn. So on the basis of this, again, if you see that if you try to replace dt here, so what we are going to get the value? Dt will going to become here dx upon 2 pi fm. So that's why in place of dt, it's written dx by 2 pi fm. Okay. And in place of 2 pi fmt, x is written. So that's why this fm get cancelled. And here what we have? 2 pi. Okay, so now this integral of this equation is what? This is the nth order basis function. Later we are going to see again in detail various properties of the Bessel function. So this is the first kind and argument beta. So finally this Jacobian basis function is written represented here as the Jacobian n of beta, that is 1 by 2 pi integral minus pi to plus pi exponential j beta sine x minus nx into dx. So here in the previously in equation 4 we are seeing that this limit is minus fm by 2 plus fm by 2, but we have taken x equal to 2 pi fm t, so that's why limit has also changed here. Okay, that all you can do a small exercise, or limit has changed here. Already we have seen how we got dt equal to dx by 2 pi fm. So similarly, if you see the value, what was the t expression here? That is the value 2 pi fm we have multiplied by t. So this is the minus 1 by 2 fm. So finally, what will happen here? fm will cancel, 2 cancel, so we get the minus pi. So similarly, upper limit is going to become the plus pi. So this Jacobian function you need to remember. So now this equation 6 can be written with the help of Jacobian. So Cn equal to AC into Jacobian of beta. So now we are going to substitute this Cn value in the equation 3. So finally we have S approximate of T equal to AC summation of this. So here Jacobian function is used. So now again this one equation 9 we are going to substitute where in the first equation where we have considered this as approximate of t. So that is going to give us the equation 10. And here we are focused only on the real part. Okay. So what is the real part of this? Exponential of this is what? E to the power I theta, again cos theta plus I sin theta. So that's why here we have cos 2 pi fc plus n fm into t. So this is the modulated wave, what we have here in equation 11. Now, if you want to get the Fourier transform of equation 11, so that is going to be the frequency domain. So in the amplitude modulation also we have seen how we are getting the frequency transform of that one. So this is AC by 2 summation n equal to minus infinity to plus infinity Jacobian of beta. And here we have Fourier transform, how used to write earlier del of f minus fc plus del of f plus fc. So in place of fc what we have? fc plus nfm. So that you can see from here. Okay, fc plus nfm is we have as the fc here. Now this is the Jacobian function for the different values of this. N is represented here. So when here n is 0, so this is the waveform. N is 1, n is 2. Like this for different values of beta here in the x-axis, and Jacobian n of beta is taken in the y-axis, and we have different waveform. So important question again, it is can have short question about the properties of the basis function. Okay. So these properties are Jacobian n of beta is minus 1 to the power n Jacobian n of beta for all value of n, positive as well as negative. And Jacobian of beta for n equal to 0 is 1. Jacobian 1 of beta is beta by 2. And Jacobian n of beta is equal to 0 when n is greater than 2. And this is also important, summation over n equal to minus infinity to plus infinity. We have Jacobian n square of beta equal to 1. So this property we are going to use when we'll try to find the power. So here just now you see that we have calculation of the average power in the FM signal. So that is the half AC square summation of this one. So this value is going to become equal to 1. So this is what AC square by 2, which is same as the power of the carrier signal. So here we see that this is del f is the frequency deviation for beta value is 1 and here beta value is 2. So here you can see that how this 2 del f is going to decide the how many side bands are there. Again, little bit later we are going to see in detail for different value of beta why we have this much of the side bands, like here 3, why we have here 5, all these things we are going to discuss. So here what we have, okay, del f is the frequency deviation. Now it is important separate question. They will ask you about transmission bandwidth of the FM signal, or sometimes objective question also will come from here. Like what is the transmission bandwidth? What is the Carson's rule? Okay. So this for the FM signal here, it has infinite number of side frequencies, but it is limited to the finite numbers. So that depends upon the different value of the beta. And here this bandwidth is going to become equal to the 2 FM. FM is the message signal frequency. So finally here transmission bandwidth. So the bandwidth, okay, that is one is the bandwidth 2 into FM. Another is the transmission bandwidth. Okay, that range of the signal in which it is being transmitted. That is the transmission bandwidth is generated by the single tone modulating signal is what here? BT equal to 2 del F plus 2 FM. So that we have seen there. What is the 2 del F? How you are going to decide? So here if you take the 2 del F as the common, so you'll have expression like 2 del F inside the bracket 1 plus 2 FM by 2 del F. Okay. So 2 will be cancelled. Letter del F by FM is what here? Beta. So that's why we are getting 2 del F into 1 plus 1 by beta. So this is also called as the Carson's rule. So this is also objective questions. So here again beta can be we can take approximately as 2 n max FM, where n max is what? Largest value of the integer n that satisfy this Jacobian function. Now you have different modulation value, that is the beta value is different. What is the 2n max value? This is only for the understanding purpose. Then we have deviation ratio D. What is this? It is the ratio of del F, okay, which correspond to the maximum amplitude of the M of T to the highest modulation frequency. So that is also important. So D is the del F max by W. Okay. Now we have again already we've seen the power there, calculation of the power in case of modulated wave. So we are talking about the average power. So that is going to become here 1 by 2 AC square. Since Jacobian, this value is equal to 1 by the properties of the Jacobian. So this is the power, average power. Okay. So which is same as the carrier power. In the unmodulated carrier power is same. So now here, if you see that an ideal FM has infinite bandwidth, some properties are here. For a small value of beta, wideband FM reduces to narrowband FM. Again, the carrier component of wideband FM is the function of index modulation. Okay, and now we are going to see that this is for understanding purpose, that if any numerical is going to come, you can see variation in the amplitude and frequency of modulating signal. So one time here already we have seen that we have del F is kf into m. So you have seen that it is independent of the frequency. So two different conditions we are going to see. When FM is constant, m is variable. Later we'll see that m is constant and FM is variable. What is going to happen here? So when FM is constant means FM is constant. So that is finally, if you see that transmitted bandwidth, what we have calculated earlier, okay, and this is the 2 del F. So since AM is variable here, so del F is going to change. Since del F depends upon the amplitude of the message signal, it doesn't depend upon the frequency of the message signal. So even FM is constant, but M is variable, so del F is going to change. So here for the beta equal to 1, we have 3 side bands and you can see that 2 del F, okay. But here in case of beta equal to 2, we have 4 side bands and you can see that how this 2 del F has changed. So that is more wider here, and the difference between 2 side bands is what here? FM. So here also you can represent it is also again FM, it is again FM, this is also FM like this, okay. So now if second case FM is variable but M is constant. So M is constant means del F is going to be constant. So again beta is 3 side bands. So now this 2 del F is not going to change. What is the variable here? FM is variable. So beta equal to 4. Again you see that here 2 del F is not going to change. So FM is reduced. Okay. So like the situation is that. Now very important part we are going to see here, that is the numerical. Okay. that you must have to cover. If question is even the external exam or sometimes in the gate exam, this numerical is going to be important. What is the first question? Consider an FM signal defined in direct analogy with AM signal as, so that is AC cos 2 pi fc into 1 plus mu m of tt. What is the instantaneous phase angle of the FM? That we need to find. And here they're asking take m of t as it cos 2 pi fmt. So they're asking instantaneous phase angle means theta I of t we have to find. So if you compare here this extended equation of this FM modulated wave, what we have S of t equal to AC cos of theta I of t. So what are things is there? This is going to become here theta I of t. That's why we have written theta I of t equal to 2 pi fct inside the bracket 1 plus mu m of t into t. Now m of t value is substituted, that is the cos 2 pi fmt. Now we'll separate these two terms. Okay, so we have 2 pi fct and this is second term. Now we are trying to find the instantaneous frequency. So already you have seen, we are going to how we have obtained earlier in the same way here. We can multiply here this value if fi of t is given, but here theta I of t is then. So we have to differentiate theta I of t with respect to time and we have to divide by 2 pi. So finally here 2 pi fct differentiation is 2 pi fc. Again here if you see that again you have like we have u into v. Okay, this is the 2 pi fct again cos 2 pi fm. So on the basis of this how we have u equal to du by dt. So if you have in the terms of u into v, so how you are going to differentiate? This is going to be u into dv by dt plus v into du by dt. So on the basis of that, here what we'll have, first we are considering this one as suppose as the v or anyone. So first we are differentiating 2 pi fct here. So we have 2 pi fc cos 2 pi fmt is taken as the constant. In the second time what we are doing, we are going to differentiate cos 2 pi fmt. So that differentiation is the minus sine 2 pi fmt multiplied by 2 pi fm. That is the differentiation of cos 2 pi fmt. After that, we are going to rearrange this expression. Okay, so we have these values. That is the instantaneous frequency. So we have to be basic knowledge how derivation is being done. Then we can solve this. Next, we have second question. The maximum deviation in the commercial FM is del F equal to 75 kilohertz. Determine the permissible range in the maximum modulation index for the commercial FM. So here that has 30 hertz to 15 kilohertz modulating frequencies. So here multitone is there. And we have second question in narrowband system that allows maximum deviation of 10 kilohertz. And another is 100 hertz to 3 kilohertz modulating frequencies. So two different situation is given here. So in the first, what is written here, del F is how much? 75 kilohertz. So again, now here we have to find the what they're asking, commercial FM having. So find the modulating frequency range is given. Again, narrowband is given here that allows this part. Okay. So we have to find here first beta value. Again, we'll discuss about the narrowband FM. Okay. So now they're asking the permissible range in the maximum modulation index. So we have del F is 75 kilohertz and beta, we know that beta is going to be here, okay, del F by Fm. So del F by Fm is the beta value. So finally, one substitute the value of del F here, okay, and divide by Fm. So we have 2500. Again, for the different frequencies, one is what we have substituted 30 hertz. Next is the 15 kilohertz. So next we substitute the 15 kilohertz. So that is going to become 5 here. So that is the different value of beta here. Next we have narrowband FM. So here del F is given 10 kilohertz. Beta again we have 100. Again beta is going to be the 10 by 3. So range of frequency is given. For the 100 hertz, this is the beta. For the 30 kilohertz, this is the beta. And here deviation frequency is given 10 kilohertz, so 10 into 10 to the power 3. So it is completely formula based. So simply here again, third question we have. So one that is a 100 megahertz carrier has the peak voltage of 5 volts. So amplitude is 5 volt here. The carrier is the frequency modulated by sinusoidal modulating waveform of frequency is 2 kilohertz, such that frequency deviation is 75 kilohertz. The modulated waveform passes through the zero and is increasing at t equal to 0. Write the expression for the modulated carrier waveform. So here discussion is about the modulated waveform. Okay. So what is given? It is going to pass through the zero and increasing where? At t equal to 0. So we have, it is the t equal to 0 means it is the sine waveform. Okay. Otherwise, 1 means cos. So it is the sine waveform. So it is the written AC sine 2 pi fct beta sine 2 pi fmt. So here what we have? AC sine. Okay. Is not cos, AC sine. Is given here by sinusoidal modulating waveform. Sinusoidal modulating waveform. So sine waveform we have taken as the sine 2 pi fmt message signal, and beta, in terms of beta it is retained, and remaining thing is given. FC is given here. Okay, FC is 100 megahertz. Okay, so that is 10 to the power 8. Again del F 75, FM 2 kilohertz. AC is given, so beta value is del F by FM 37.5. So finally modulated wave, we are substituting the all values. Okay, so AC is given 5, so we have substituted here. FC is given 10 to the power 8, that we have substituted. Beta we calculated 37.5, and here FM is given, that is 10 to the power 3. Okay, so that all value. FM is 2 into 2 kilohertz, means 2 kilohertz is how much? 2 into 10 to the power 3. So that all value we have to substitute, and later we can simplify, that is the modulated wave. Next question again we have about similar question, a small change, that's all. So a carrier of frequency 10 to the power 6 hertz, a carrier frequency. So this is FC. Amplitude is what? 3 volts. So this is the AC. Is the frequency modulated by sinusoidal modulating signal. Again, it is the sinusoidal modulating signal. So 500 hertz. So it is going to become the FM. And a peak amplitude a 1 volt. So this is the AM. The frequency deviation is 1 kilohertz. So that is the del F. The level of the modulating waveform is changed to 5 volt peak, and the modulating frequency is changed to 2 kilohertz. Okay. So that is the FM has changed. So write the expression for the new modulated waveform. So first we'll see that what we are going to get the general waveform. We have AC cos 2 pi ct beta sine 2 pi fmt. So it is here they are not writing t equal to 0 in all. So we have taken the cos, and modulating wave is the sine. Beta is del F by FM. Del F is the kf into m. So all these things are given what we have written. So finally del F is here 1 kilohertz. So this frequency sensitivity we can obtain here. Okay, del F by AM. So we have 10 to the power 3 hertz per volt. And in the second situation, they are saying that it's going to change. AM is 5 volt, FM is going to be 2 kilohertz. So beta is going to be del F by FM. So that is we have 2.5. So that's why finally it is going to become 3 cos. AC value is 3 cos 2 pi into 10 to the power 6. FC is 10 to the power 6. It is the what we have calculated, beta value 2.5 sine 4 pi into 10 to the power 3 into t. So these are the discussion about FM signal, where we have narrowband FM, wideband FM, then we have power calculation, and we have seen the numericals. So this is going to be very important lecture for you. So please subscribe, share, and like, and write your comments. Thank you. Thank you very much.